What I have behind me is probably the world's smallest vacuum tube guitar amplifier in terms of output power and size. And in today's video I want to show you how I designed it and of course what it sounds like. This is what the circuit looks like. It's based on this 1950s tiny vacuum tube, which was designed specifically for hearing aids. So it is an audio output tube made obviously for portable devices, but turning this into a guitar amplifier is quite a stretch. At this point you're probably wondering why I even bother making this thing. Well, the thing is that I love old electronics, especially vacuum tubes, and I also wanted to take on this challenge because this tube is way too obscure to find a project online that's readily available. So this video could be the very first video online that shows you this tube in action. For scale, here's what a typical audio output tube looks like. This is an ER34 and needless to say it runs on much higher voltages, much higher currents. It gets very hot during operation, it consumes lots of power and it requires very bulky transformers around it in order to produce any sounds. And of course that's not the case with this amplifier, and even though this is on, you can touch it safely. It just runs at 30 volts and it can even be battery powered. If you're messing with audio devices at home, you probably know that connecting your guitar or amplifier to a breadboard is a pretty inconvenient task. So to solve this, I made my own adapter that can easily adapt this jack to the breadboard. It has an input, an output, and it also has true bypass, of course. The main challenge that I had to overcome in this project is adapting the tube, which is a high impedance device, to the headphones, which are low impedance. What this means is that the tube prefers high voltages and low currents, however the headphones are quite the opposite. They prefer low voltages and high currents. So to fix this, I had to find some suitable transformers for this, which is quite a challenge, but eventually I came up with this idea. By browsing an online parts supplier, I found some interesting audio transformers that are really tiny, which are the ones here. So these are two different transformer types connected in a weird series and parallel combination, which acts as a single transformer in the end that adapts the impedance to like 40k, which is the impedance that the tube sees, to something like 6 ohms, which is what the headphones see. This was accomplished using two SP13 transformers made by Triad Magnetics that are connected to two SP48 transformers also made by Triad Magnetics. The primaries of the first two transformers are in series. Each one is 20k, which gives us a total impedance of 40k into the anode. However, their output impedance is 800 ohms, so it's not suitable for driving the headphones directly. So for this I needed another pair of transformers which take the impedance down from 7.5k to 12 ohms. So for the best matching, I decided to run the secondaries of the SP13 transformers in series and the primaries of the next two transformers in parallel. This is not ideal, but it works. In terms of the output secondaries, the schematics shows them in parallel, however, in the end I decided to run them in series and this increased the output power. But how do we know that our value of 40k is acceptable for this tube? Well, this information can be derived from the output characteristics of the tube by drawing a load line. Let's start with what the output characteristics are. Well, on the output characteristics, we look at the anode current with respect to the anode to cathode voltage. Since this tube is a pentode, this family of curves could be familiar to you because this is exactly what you would get by driving a bipolar transistor at various base currents. What these curves tell us is that once we get away from this region right here, which is pretty non-linear and weird, the tube basically acts like a current source. It's almost horizontal, regardless of the anode to cathode voltage. So why do we have multiple characteristics here? Well, that's because the tube was driven at various grid voltages in order to figure out your best bias point for your circuit. So as you can see, when the grid is really negative at -2 volts, we get a really low anode current. However, as the grid voltage increases, the current gets higher and higher. And the maximum grid voltage is 0 volts, and at this point the tube basically conducts as best as it can. It is important to mention that this curve stops at a VG1 voltage of 0 volts for a reason. That's because you are not allowed to drive the grid positive. Once you drive the grid positive, it basically becomes a secondary anode, it starts drawing current, and that's really bad and it can damage the tube. By the way, this tube is a pentode, so we have 3 grids to take care of, so you may be wondering what happens to the other grids. Well, VG2 is right here, so the second grid is biased at the positive voltage of 22.5 volts, so this one is a fixed voltage, and grid number 3 is internally connected to the cathode, so we don't need to worry about that either. And finally, here's our chosen load line. To draw this, first of all you have to decide the anode voltage, and in my case I decided to run the tube at 30 volts. So this gives us the bottom right corner. Why 30 volts? Well, the maximum voltage is 45 volts and I decided to leave some margin, so I'm running the tube at 30 volts. So what about the slope of our load line? Well, the slope is given by our 40 kilo ohms of AC impedance, and this is the line right here. So to know where this line ends, you just have to use Ohm's law and calculate the current at 30 volts for an impedance of 40 kilo ohms. And this gives us a value of 750 microamps, which is somewhere around here. So in order for this to work as an amplifier, we need a load line that has a certain slope to it, so it cannot be straight up and it cannot be horizontal, obviously. So you have to make the tube kind of swing through these states, from going to close to the maximum current maybe and close to cutoff, with some voltage change in between and current change in between. And here you could also see why it doesn't work with headphones. So by connecting the tube to a 32 ohm load like the headphones, our load line would basically be straight up. And what this means is that the tube would always have 30 volts on the anode with respect to the cathode, regardless of the grid voltage, which means that the tube will have 0 gain. So this is where our transformer comes in. By the way, if we say 40k here, this is an AC impedance, assuming that we have the right load at the output, so this is not a DC load line. If you were to measure the resistance of the primary of the transformer, that's definitely not 40k, it's a much lower impedance, and yes, for that the load line is almost straight up as well. But as soon as the AC load line is okay, the amplifier is going to work. So what you can see from a reasonable load line is that as you vary the grid voltage, the point on our load line, which represents the state of the tube, also changes. So if the voltage goes higher, we go higher and higher on this load line, and as the voltage goes lower, we get lower and lower on this load line. So the next step is to choose a bias point, and we do that by choosing a convenient point which is somewhere in the middle of this characteristic that allows the tube to swing both up in current and low in current. So we don't want a point right here because the tube is almost in cutoff, so it cannot go much lower than this. And we also want to stay away from the top region because we cannot drive the grid positive and we cannot exceed this current. So a point somewhere around here is acceptable. That's why I chose this point, which is at around 300 microamps of anode current. And by looking at the required grid voltage for this, we can just draw a straight line from here, and this puts us at around 600 millivolts. You'll see why this is important later. This finally takes us to the complete schematic, which is a typical audio amplifier with a cathode degeneration resistor and a cathode bypass capacitor. The only trick with this, if you're not familiar with vacuum tubes, is how on earth can the grid one be negative when we only have positive voltages in this circuit? Well, this is a really neat trick that we always do with vacuum tubes, which is grounding the first grid with really high value resistor and then driving the cathode positive, or actually letting it self-bias, as you would say. So what we do is, instead of grounding the cathode, we connect it to ground using a resistor, which means that based on the cathode current, we will have a voltage drop across this resistor, which will make the cathode positive. So if the cathode is positive but the grid is at 0, this basically means that the grid is negative. It's not truly negative, but it's only negative with respect to the cathode, and that's all the tube cares about. So how do we know the value of this resistor? Well, this is where the output characteristics help. If you remember, we said that the negative bias on the grid needs to be around minus 600 millivolts, which means that the cathode needs to be at positive 600 millivolts. And we also know the cathode current from the characteristic by approximating it to the anode current, which means that here we need 600 millivolts when 300 microamps pass through the resistor. And based on Ohm's law, this gives us a value of 2K. However, this resistor also limits the gain, so in order to get the maximum gain out of this stage, it's a good idea to bypass it at AC with a capacitor. So this is just for increasing the gain. So here's the circuit on a breadboard. Let's just turn it on and see if our math is right. First of all, since this is a vacuum tube, we need to power the heater, and since this was made for portable devices, the heater was designed to be run by a single battery, so that's easy. And now this is an active device. For the anode supply, I'm using this general purpose unit power supply. It's set to around 30 volts. So now it's time to monitor the bias point on these two multimeters and see where we're at. So this is the total current on this multimeter, and this is the cathode voltage. Let's connect the amplifier to the anode power supply and see what we get. Look at this, it's bang on. I cannot believe it. This is very close to 300 microamps, and this is very close to 600 millivolts, so our circuit works perfectly. And now it's time to see how much power we can get out of this thing, but before that, let's look at the limiting factors. So what limits the power here is basically the headroom of the amplifier, meaning how much can the input swing before the amplifier distorts. This would be one of the main factors. Here, if the grid sits at around minus 600 millivolts, it can only swing up 600 millivolts from here until it reaches 0 volts. Once that happens, going beyond that point turns the grid positive, which will make it conduct, and it will make the tube distort horribly. So this limits the input amplitude. And also, driving the output transformers at a really high current can make them saturate, and that will also cause distortions. So these are the main limiting factors of such an amplifier. In this case, I think the tube saturates before the transformer. So to test the amplifier for the maximum power, we need a dummy load, which is a 12 ohm resistor in this case, and we need a signal generator that produces a 1 kHz sine wave. And then we will increase the amplitude until the amplifier distorts. Let's start with 650 millivolts peak to peak. Okay, it looks pretty linear, and now we have to increase the amplitude slowly and look at the waveform on the oscilloscope. Okay, starts to look weird. Let's increase it even more, and now it definitely distorts. So at around 680 millivolts it really distorts, and this is really noticeable if you take a listen. So here's the amplifier at 650 millivolts, and here it is at 700 millivolts. So it doesn't have any of that nice tube distortion. This one distorts really suddenly and it sounds really bad. So at the output, the maximum clean amplitude is around 175 millivolts RMS, and if we drive that into a 12 ohm load, this means that we get a power of 2.5 milliwatts. Nice. Even though this is a really small power, it's enough for playing guitar and listening to that into your headphones. So I did some more testing with the guitar, and I noticed that the amplifier changes the tone a lot. So the amplifier is on bypass now. This is what it it sounds like. So this is the guitar straight into the audio interface. Now let's activate the amplifier and see what it sounds like. First of all, this is not so loud, so it attenuates the sound, which is really weird for an amplifier. So I have to compensate for this with the guitar knob, and now it's on full volume, but still it's not that loud, and still we have a totally different tone. So I think this lacks low end, even though the high end is there, so it's really interesting. So I think it would be an interesting idea to have a look at the frequency response. To do this, I'm using this signal generator, which is configured to produce a linear frequency sweep, starting from 100 Hz and going all the way up to 40,100 Hz. And this sweep will help us look at the frequency response on the oscilloscope by synchronizing the oscilloscope to the sync out of this generator. So this is what you can do if you don't have a spectrum analyzer with a tracking generator, which I don't have. And this is what the sweep sounds like. It's really annoying, but fortunately we don't have to listen to it. Here's the response, and it pretty much confirms my suspicions. So as you can see, it's nowhere near flat, unfortunately, and since we know what the settings are, we know exactly how many hertz per division we have here. So we have 4000 hertz per division, which means that at the start of the sweep we have around 100 hertz, and here we have around 4100, which means that below 4 kilohertz you can see that the frequency response just drops. So we don't have that much low end, unfortunately, and the response is nowhere near flat, and it extends beyond the audio bandwidth, which is also not a good thing. So we should have a low pass characteristic here, and it should attenuate higher frequency, because otherwise it could be sensitive to radio frequency interference, I guess. I was also very curious to see what the frequency response would look like with headphones, and here it is. It has an interesting kink here, which is some sort of mechanical resonance probably that comes from the headphones. And I noticed that the amplitude is much higher. I had to reduce the sensitivity here, which means that the amplifier really prefers inductive loads and headphones instead of the 12 ohm resistor that I used as a dummy load. So this increases the output a lot, but still the frequency response is nowhere near flat, and still we are losing low end. And I'm sure you are curious to see how much the frequency response extends. So I extended the sweep to 100 kHz, and here it is. As you can see, we have a peak at around 50 kHz and then it starts dropping. In case you're wondering, yes, the tube is very microphonic. This is another undesirable property of vacuum tubes. So that's about it, and now I'm thinking if I should build this into a more permanent form, like designing a PCB for it and making it a battery powered power supply so that this looks more like a product. I'm not sure if such a toy project would be worth it, but yeah, please let me know in the comments if you would do that, and please let me know in the comments how you would improve this circuit. That's about it for now. Bye.